Hey everyone, welcome back to discussion number 25. We're going to start looking at problem 48 on page 483. So we're given that an object has this mass, 0.2 kilograms, and we're given that it is oscillating in the x-hat direction. We're also told that it has a frequency of 25 over pi hertz, and that at one particular moment it has total energy with kinetic energy 0.5 joules plus potential energy 0.4 joules. And then we are asked to find the amplitude of the oscillation. Well, we can go about this. So let's recall what an equation for position function is for a wave, right? We had y max, which is your amplitude, times, what was it, cosine omega t minus phi, right? Just leave it as time. Okay, so now we want to find what is this. Oops, we want to find what is this, right? So now we can look at this using the energy, since we're given a moment in time where the energy is equal to these things. Probably we can use conservation of energy, and that's what I intend to do. So we're going to say kinetic energy is equal to half mv squared, right, is equal to half m dy dt all squared, right? And from the last discussion we actually did this. We found the velocity function as a function of time using this equation. So now we have y max squared, right, omega squared, and then we have sine squared omega t minus phi. So that's your velocity. This would be your velocity, right? And then we had half m. So here's your kinetic energy. Okay, so now let's find, what do we have for an oscillating spring? We had half kx squared, right? Half kx squared. And that's going to be equal to half, where k is equal to, if we recall that we had this relationship, and so that means that k is going to equal m omega squared. Okay, so now we have m omega squared, half m omega squared, and then we have cosine squared omega t minus phi, because it's just the position function. Oh, also y max. Can't forget to put that in there. So now we just sum this up, because what we're looking for is total energy, right? So we have one instance which we're given here. This, we'll call this E naught. This is the instant. This energy is going to have to equal your final energy, right? Because that's what we're given. And if we're conserving energy, all the energy should be equal at every moment. So, okay, so now we have E is equal to kinetic energy plus potential, and that's going to be equal to, if we look here, we can actually factor some stuff out. We have y max squared, omega squared, m 1/2, m 1/2. So we can factor all of that out. 1/2 m omega squared y max squared, and then we have sine squared omega t minus phi plus cosine squared omega t minus phi, and then that actually will just go away, right? That goes away because that just equals 1. So now total energy is equal to half m omega squared y squared max, y max squared. Cool. So now we can use this information. So let's set this equal to what we had here. So we had E initial is equal to E final, right? And that's going to be, what was it? It was let's look up here. What did we have? For kinetic, we had 0.5, and for potential, we had 0.4. So that's 0.9 joules, right? So 0.9 joules is equal to half m is 0.2 kilograms. Omega, not using this relationship right now. So omega we can find from the frequency. Okay, let's just write this in here. Omega omega squared y max squared. And then let's just solve. I'll solve for y max real quick, and then we can plug in. I'll show you how to find omega in a second. So we're going to have 2 times 0.9 joules. Okay, 1 over 0.2 kilograms, 1 over omega squared, and this is all going to be under a square root, right? So now that's what we're looking for. We're looking for, what does it say? Amplitude of oscillation, which is this y max is going to be your amplitude. So omega. So here we have this relationship, right? 1 over t is equal to frequency. So that's a basic identity that we all know now. And we know that t is equal to 2 pi over omega. So then 1 over t is equal to 1 over 2 pi times omega. Oops. So now we have omega is equal to 2 pi times the frequency. So, and I got that all from this basic relationship here. Okay, f is equal to 1 over t. T is equal to 2 pi over omega. So I just solved for 1 over t because that's what we have here. Plugged it in. Then we solved for omega. So these are standard identities that you can find in any physics book. Okay. And what was f? F was 25 times pi. So this is going to be equal to 2 pi. No, sorry, 25 over pi. 25 over pi. Pi is canceled. This equals 50 radians per second, right? Okay, so now we know what y max is going to be. 2 times 0.9, 1 over 0.2, 1 over, we'll call this 50 squared. Just put that under the square root 2, why not? And then we get a value of 3 over 50 meters. It's roughly 0.06 meters. Okay, and we can check the units as we should. So here we have, what is this, 0.9, that's joules, so that's Newton meters. So we have kilograms, meters squared, over seconds squared. This is in joules, okay? Okay, and then we have 1 over 0.2, 1 over kilograms, and then we had 1 over seconds squared, which gives you seconds squared. These cancel out, and this is all under square root. That gives you meters. So that's right. So I encourage you to check that stuff on your own as well. All right. So get rid of this. Next problem, number 49 on page 483. Okay, so we have this car. It's sitting on its shocks, right, without any extra mass. So the car weighs this, and it's sitting on the spring, but we're going to model this as the system initially, right? So we say that there's really nothing going on here. So we're going to say that the load here is equal to 0, because the car is just sitting there all the time like that. So this is nothing new, okay? And then this is a spring constant K. We want to find out what that is. So when these 4 people jump into the car, well, let's say they gently sit down in the car, right? And then it displaces 15 centimeters only. It just goes down a little bit, okay? So now we have a load. Now our mass is 280 kilograms, right? And so now we also, since we've introduced a mass into the system, we have a weight force going down, and we're going to have a spring constant pushing up. So this is going to be your Hooke's law force, right? So now, once they got in and pushed this thing down 15 centimeters, it's just sitting there. So now we're in equilibrium again with a spring potential. So that means we have a force pushing up and a force pushing down, because we know gravity is acting on this system, and we know that the spring force is pushing up. So that means we're going to say that nothing is happening, but we do have a balance of forces where we have mg and then we have minus kx, right? Or if you wanted, yeah, that's good. So then we say mg is equal to kx. And now we can find our spring constant. That leads us to a spring constant of x over 280. Oops, that's wrong, sorry. Some bad algebra there. So we have 280 kilograms times 9.81 over 0.015 meters. Cool, so that gives us a spring constant that we can use. Now we want to find, we're asked to find what is the damping constant, because this is a damped system. That's what shocks do. I mean, it's not just a spring. There's like a piston around it with a damping device, okay, so that we don't, because otherwise if you don't have the shocks, then the springs just bounce up and down when you hit a bump or something. There's, you know, then the people in the car are just bouncing around and hitting their heads, and that's not cool. So you put a shock absorber, right, and that kind of minimizes the bounce that you get. So we're asked to find what is the damping constant. We're given a relationship in the chapter summary that we can use. There's a derivation in the chapter as well. If you want to go through that, it's a good idea. So now we have, okay, so now we have 2 times the mass. And this is going to be for the total system. So looking at this, we were able to determine the spring constant here, K, using just the initial mass that we placed onto the spring to knock it out of equilibrium, right? Its initial equilibrium. Okay, so now we did that, and we want to look at the system as a whole. So now we're going to use both the mass of the car and the people in it. Excuse me. So that's going to be Mn. We're going to call Mn is going to be M1 plus M2 is equal to M net. Okay. Times omega, and omega is what it's going to be. Recall that omega is equal to the square root of k over m. So now we have the square root of this k over the total mass. So this is going to be k, spring constant, over the mass of what's in your system. Okay, so what does that mean now? We have 2 times m net times m of the people times g over x naught all over net mass. Okay, that's going to give us B is equal to 2 times, what do we have here? Let's go, okay, so 9.81 meters per second squared times 280 kilograms. So we can simplify here, this mass and this mass will give you a mass up top. It's going to be 2280 kilograms. That's the mass of the car and the people in it. Okay, and this is going to be over 0.015. So that's going to be this. It gives you a value of 4.09 times 10 to the 4 kilograms per second. So those are some pretty powerful shocks, and they have to be because you're talking about a car full of people. So that's your answer. Okay, next we're asked to find the period. Right, part B. This was part A. This is part B, and we're asked to find period of an up and down oscillation of the car after hitting a bump in the road. The shock absorbers are worn. Okay, so provides almost no damping. Okay. pretty much what we're being asked to do is just ignore the damping constant entirely, because it's saying that, okay, now there's no damping from the shocks, and like I said before, when you hit a bump, this thing is just going to bounce up and down like crazy, right? We want to know what is the period of that oscillation if there was no damping. So what is period of a spring? Well, recall that it's 2 pi over your angular, or your, what you would call your oscillation speed, right? So this is going to be 2 pi times, and also this was k over m, right? So now we have m over k. So we know what the mass is, and what the spring constant are, and what the spring constant is, right? So we can just plug this in. This is going to be total mass, and this is going to be your spring constant. So this is 2 pi times 2280 over, what was our spring constant? Over k, so that's going to give us 289.8. Okay, so this is 280 kilograms. This is also kilograms. 9.81 meters per second squared down here. Extend this, and then we have 0.015 meters here, right? Because I'm just plugging in k, 1 over k. Okay, we just plug that in, and then we end up with a value of t is approximately equal to 0.7 seconds. So once this car hits a bump and it's full of people, it's gonna, each period, each oscillation, right? Like, so every time this thing bounces, which is gonna be a lot, by the way, every time this thing bounces, it's almost 1 full second. So it's about like that. It's about like that. So 1 Mississippi, almost that. So boom, doom, doom, something like that. That's without damping. So that's an interesting problem. Moving on. Number 66. Okay, so we are told that we have a mass on a spring, and it's undergoing simple harmonic motion. It completes 4 cycles in 14 seconds. We're asked to find period, frequency, and angular frequency. So we want period, frequency, and angular frequency of the system. Okay, we've gone through this a little bit, but here it is in more detail. So we're going to have period is equal to 2 pi over omega. That's one relationship that we have. Frequency is equal to 1 over period. And then also, I guess you could say that this is equal to, what is it? 1 over t is omega over 2 pi, right? So this is these are the basic relationships that we're working with. And so you're asked to find these things. It doesn't say necessarily in this order. You could find it in this order if you wanted to. The way I did it was I just went. You can use your angular frequency, because we're told that this completes 4 cycles, right, in 14 seconds. So a normally an angular frequency would be 2 pi over one period, right? But we're told that this completes 4 cycles in your period. So then we can say that this is the case. We have 4 times 2 pi is 8 pi over the period of 14 seconds. Okay, we can do that, and this is going to give you a value of 1.79 radians per second. And then from there, you can just use substitutions. So you can say, okay, well, frequency is equal to 2 pi f, or 2 pi, omega is equal to 2 pi frequency, right? You want to find frequency, then just take 1.79 over 2 pi. That gives you a value of 0.28 hertz. This was C, I think. yeah, C, and then this was B. So I'm just going backwards. There's another way to do this, and I'll show you in just 1 second. Don't worry, I won't go through all of the details, but there's another way that you can handle a problem like this. So then for period, you just you take 1 over f. Excuse me. So then you go 1 over 0.28, and that gives you a value 3.51 seconds. You could also do it this way. You could also go t is equal to, what was it? It was 2 pi over omega, which is equal to 2 pi over what we found for omega earlier, 1.79. That gives you the same answer. Seconds. Okay, so that's how I did the problem. Was I started with this relationship here, but I think the expectation, because they ask you to find period first, is that you take. So you go A is for part A. We want to find period. You go the total time, right? The total time. We'll say total over the number of times. Right? Does that make sense? I mean, you're looking for the period, right? So this is going to be, you're approximately given, like, you're looking for units of seconds over the number of times that something occurs, right? Total time of the event over the number of total times that it's occurred, and this gives you a value of 14 seconds over, what was it, 4 cycles, and this is going to be the same answer. 3.51 seconds. And then from there, you just take f is equal to 1 over t. You get the same answer, and then you use this 2 pi f to find omega. So pretty much, there's not like one solid way to do it, but you can pick and choose. I personally found this to be the easiest way to understand it and to get through the problem the fastest. Next problem. Number 69. Okay, for the next problem, we're given a simple pendulum. So here's the ceiling. This thing is hanging with length L, 1.25 meters. That's kind of long. This has a mass, 2.5 kilograms, and it's oscillating, right? This way. We're told that at the equilibrium position, when this thing passes here, which is 0 degrees, right? When it passes this point, it's at 3.24 meters per second. We're asked to find the period, total energy, and the maximum displacement of the angle. So let's recall what is period, right? We have 2 pi, for a harmonic oscillator, it's 2 pi over omega. And we might be tempted to take omega as v over r from rotational motion, but remember, this will get you very close to the answer in this case, but this is not explicitly true. In this situation, we have an angular frequency for a simple pendulum that's given to us as omega is equal to g over L. Okay? That's for a simple pendulum. And remember, we also had, for a spring, we had k over m. These units all work out to be the same. So these are similar situations, but I mean, we need to make sure we use the one for the explicit situation that we have, which we're given a simple pendulum. Let's use the angular frequency for a simple pendulum. So let's get rid of these. This is for a spring. This is for a pendulum. Okay, so then we go with 2 pi. Let's do this, invert this, right? Over L, or sorry, G, 2 pi times square root of L over G. That gives us 2 pi times 1.25 over 9.81 meters per second. This is in meters per second squared. Okay, so we see in here units of meters cancel, seconds goes up top, and it's under a square root. That gives us units of seconds. That's what we want. So 2 pi, and then I guess I don't need to worry about the radians, and then we get a value of 2.24 seconds. Okay, pretty straightforward. I mean, as far as algebra goes, there's not much to do. You just have to make sure to recognize that we're looking at a simple pendulum and that we need to use the angular frequency for a simple pendulum, not for a spring and not for a point mass rotating around an axis, right? Okay, so that's T. So we're asked to find the total energy. Since we're given simple harmonic motion of a simple pendulum, we can consider, we don't need to really think about what is the energy going to be here, where we have some potential to fall down and a velocity moving in this one of these directions. That would be, we can do that, but that's going to be a little more complicated than we need it to be. So what we can do is, since we're told the velocity at equilibrium position, so once this thing flies here, it's 3.2 meters per second right here. So let's look at this. Let's draw another picture. So here at the equilibrium position, oops, this thing is traveling at 3.24 meters per second. Okay? So this has, because we have a velocity, we have some kinetic energy, right? So Ke is going to be equal to 1/2 mv squared. Now, is there any potential at this point? Is this thing, can this thing go any lower? I mean, if it fell off, if the mass were in any danger at all of falling off the string, I guess we would have to consider that it's mgh, where h is above the floor or something. But that's not the case. This is a simple pendulum. It's ideal. So this is at h is equal to 0 right here. Okay? If this swings up to this position, then we definitely need to consider mgh, where h is this distance here, because it's going to swing down, and h would be this distance here, right? But guess what? It's not. So we don't need to consider that. So really, total energy is just going to be 1/2 mv squared for this position, which is 1/2 times, what is m? M is 2.5 kilograms. 1/2, 2.5 kilograms, 3.24 meters per second, all squared, and that gives us a value of 13.1 joules. That's the total energy. Right? We're using conservation of energy. We're not losing any energy in this system. It's just going to continue oscillating. Okay? And because of that, we found this value. That's your answer. Okay, next we need to find maximum angular displacement. Okay, well, so we can use conservation of energy similarly to how we just did to find the total energy value, right? So what we can do here, we'll draw another picture here, because drawing pendulums is fun. So here's where it has maximum kinetic energy, right? At this point, we just went over this. Kinetic energy is at its maximum as it's entering this point of the swing. When it comes up here, or also over here, then we have maximum potential, okay? This is all fairly familiar. So here we have maximum kinetic. So now we can consider this conservation of energy theorem, right? Where this has no kinetic energy, or what did I say, maximum? This is maximum potential. I'm not sure if that's what I said. But now we consider up here there's no kinetic energy, only potential. Down here there's only kinetic, and I said that backwards again. There's only potential, no kinetic. Down here there's only kinetic, no potential. I think I got it right this time. So now anyway, the point is, initial energy is equal to final energy because we're using conservation laws, and this is equal to the potential up at the top, right? So now we know what this is already. We just went through this and found this value. You could plug in 13.1 joules here and solve. But the problem is, you could solve for h, right? So if you wanted to do that, you could go 13.1 joules over 2.5 kilograms, right? Over 9.81 meters per second squared. That's going to give you h. but we're looking for maximum angular displacement. So what is h? So what do we want to do here? Well, remember this is length L. This thing has to travel down here, right? So this potential, we're saying, has to travel mgh, where h is this height. So this is h down here. Well, what is that in terms of variables that we can actually use? We know what L is, right? We want to find theta. We don't know what theta is. So then this distance here is going to be L cosine theta, right? Because this is L and this is theta. So we have L cos theta. Here's L. And then that means that h is going to be, so if we take this and bring it all the way down here, this total length here is L. So that means if we're looking at this relationship that h is equal to L minus L cos theta. Okay, so that's what we get. So that's what this is, L minus L cos theta, or L1 minus cosine theta. So if you went ahead and started plugging everything in already, that's fine. You can still solve for theta using this. You know what L is. It's 1.25 meters. I like to do it more analytically first, just because it makes things easier at the end. 1 minus cosine theta. Because otherwise you kind of get into a little bit of a mess if you start doing this. You can do it, no problem. I mean, you could do it, no problem, but I run into a lot of problems when I start plugging in things early. So here's what I want to do. I want to solve for theta. So remember, we're using our conservation of energy law. Here's kinetic energy, and now we have mgh, where h is L 1 minus cosine theta, right? We just solved for that using this relationship here. Okay, so now, well, let's just cancel m, because we don't need that. 1 over 2 v squared over g times L is equal to 1 minus cosine theta. Well, that means that cosine theta, so now we have cosine theta is equal to 1 minus 1/2 v squared over g times L. And that means that theta is equal to cosine inverse of 1 minus 1/2 v squared over g times L, which is going to be equal to 1 minus 1/2 3.24 squared over 9.81 times 1.25. Right, and then anyway, this gives you a value of 0.962 radians, which also comes out to be 55.12 degrees. Okay, and that is your answer. Okay, thanks. I think that's everything. Yep, thanks. See you next time.